Hi everyone, let us discuss this example. In this example, we are going to find the value of surface integral of a scalar field. In our previous video, we have already seen the definition of surface integral of scalar field. Let me write it first. So we know that double integration f over s. F is a scalar field and s is a given surface. So to find the surface integral of a scalar field, first we should know parameterization of given surfaces. So here I consider phi be a parameterization of this surface S. Then we can write double integration f of phi of uv. This phi is a parameterization. It is defined on domain D. So we solve this double integration over D. After that, norm of phi u cross phi v, it is also required, and after that we write du dv, right? So this is the definition of surface integral of a scalar field. So let us write what is a given function. Okay, so in a problem they have mentioned scalar field f is in this way they are defined. So let me write, we have f of x y z is equal to x plus y plus z. I have written a given scalar field. Now we have to focus on a given surface. So what is the surface? They have clearly mentioned S is a cube. So let me write here S is a cube centered at the origin. That means at the center of that cube we get origin. We have that origin getting. So after that they have given some inequalities. See, when we have inequalities, to find the surfaces or to find the curves, we replace that inequality by equality, so we will have, okay. So minus 1 less than or equal to x, that means we replace inequality by equality, so we'll have x is equal to 1. So let me write here x is equal to minus 1. Here also I will do the same, okay. So x is equal to 1. For second inequality we will have y is equal to minus 1, y is equal to 1, and from last z is equal to minus 1, z is equal to 1. That means that surface S, that cube, is made up of this 6 different surfaces, right? So let me show here. We have a cube like this. You can easily see how many surfaces it has. It has total 6 surfaces, okay. So on 4 sides we will have 4 surfaces. At the top we have 1 surface and at the bottom we have 1 surface. That means total 6 surfaces we have, right? So this cube is also made up of these 6 surfaces. X is equal to 1 means what? It is a plane parallel to yz plane, passes through x is equal to 1. Similarly, x is equal to minus 1. It is also plane parallel to yz plane but passes through x is equal to minus 1. Similarly, we can say about this y is equal to plus minus 1 and z is equal to plus minus 1. So let me draw that cube here so the picture will be clear to you, okay. Okay, so let me draw cube here. So we have this type of cube. It has total 6 surfaces. Let me draw. Okay, so this type of cube we have. Okay, I am showing that side in this way. At the center of that cube we have a origin 0, 0, 0. So we have a y-axis like this. This is our y-axis, right? Okay, this is our z-axis and this is our x-axis. Okay, so this surfaces, 6 surfaces we have. So let us call them as S1, S2, S3, S4, S5 and X6. So x is equal to 1. Okay, this front surface I am calling it as S1. Same surface, one more surface we will have at the back side of that cube. So at x is equal to minus 1, I am calling it as S2 on the back side of that cube, getting? So at y is equal to 1, we have one surface, I am calling it as, this is at y is equal to 1. So this is S3. On this side we have surface, that is S4. At the top we will have one surface, I am calling it as S5, and at the bottom we have one surface, I am calling it as S6. So total 6 surfaces we have. So here we have to solve that surface integral of a scalar field over S. But see, S is made up of 6 different surfaces, S1, S2, S3, S4, S5 and S6. So therefore we can write, so let me mention here S is made up of 6 surfaces, say S1, S2, S3, S4, S5 and S6. So therefore we can write, therefore surface integral of f over s is equal to double integration over S1 plus double integration over S2, double integration over S3 over S4 over S5 and over S6. That means we will find surface integral for 6 different surfaces separately. We will solve and at the end we will add them and we will have the required answer. Okay. So this is our strategy to solve this problem. Make a screenshot of it first, then I will go further. First of all, I am going to find the value of surface integral over this surface S1. Okay. Surface S1, that means the front surface, okay, which passes through x is equal to 1 and parallel to yz plane. So let me write the equation of S1. Equation of S1 is x is equal to 1, right? So the most important thing is to find parameterization. Without parameterization, we cannot find surface integral of a scalar field. So let us find parameterization. Parameterization of S1 is, okay, we will denote it by phi. See, the main purpose of parameterization is to reduce parameters, right? So total 3 variables we have x, y, z. So we want to reduce the parameters. So we want the entire equation or whatever you say that in 2 variables only, right? So equation of surface S1 is x is equal to 1. That means that is fixed. X is 1. So that's why we can express it in terms of y and z. So phi of yz is equal to x. What is our x? 1, and y and z are 2 variables. Okay. So after that we want the limits of y and z. As you can see here, value of x is fixed, which is 1, and y can vary from -1 to 1. Similarly, z can vary from -1 to 1. Since in a problem they have mentioned y varies from -1 to 1 and z also varies from -1 to 1. So let me mention here y varies from -1 to 1, z also varies from -1 to 1. So after getting parameterization, the next task is to find derivatives with respect to y and z, since we have 2 variables y, z here. So derivative of y with respect to y, component wise derivative I will take, derivative of 1 0, y 1, derivative of z 0. Since we are taking derivative with respect to y, so z is a constant, derivative will be 0. Phi of z. Now I am differentiating with respect to z. So that's why derivative 0, derivative 0 and derivative of z with respect to z is 1. After that we want cross product. So phi y cross phi z. So you know well how to find cross product by using determinant. Okay. So I am taking determinant here. The first row is obviously ijk, second row phi y. So yes, 0 1 0. Second row, third row 0 0 1 0 0 1. So let us solve the determinant. Okay. So we have already seen how to find the value of determinant I. Product of this to 1, product of this to 0, minus j. Always we write the minus sign for the middle term. J, 0 into 1, 0, 0 into 0, 0, plus k, 0 into 0, 0, minus 0 into 1, 0. So finally I can see we have, let me write here, we have some space, let us use. Okay. So simply we can say this is I 0j 0k. So in this way we got a cross product. Okay. So after that we have to find its norm. Let us find norm. Norm of phi y cross phi z. So the definition is quite simple. Square root of multiple of I 1, its square is 1. Multiple of j 0, square will be 0. Multiple of k 0, square will be 0. So its value is 1. After that we want f of phi of uv. So let me find f of phi of uv, but here we have a yz, so that's why I'm writing yz. So this is equal to f of phi of yz. What is this definition? 1yz, 1yz, right? So I simply put the definition of phi there. After that we have to operate f. Definition of f is quite simple, x plus y plus z. Simply we have to add these three components. So if you do here, so 1 plus y plus z. Okay, so everything is ready now. So simply we have to apply the definition of surface integral of a scalar field. So then let me write double integration of f over s1. So definition says double integration f of phi of yz norm phi y cross phi z and dy dz, right? Since now we have two variables y and z. See, limits of y I will write here, which are -1 to 1. I have already written here. Limits of z -1 to 1. So let us put the values -1 to 1, -1 to 1. Its definition we have got here 1 plus y plus z. Value of norm is 1, so I will not write anything, and this is dy dz. Okay, so now we have to solve this integration. See, but there is no more space to write. Make a screenshot of it first, then I will go further. Okay, so let us find its value. Okay, let us solve this integration. See, this is equal to integration -1 to 1. As you can easily see here, we have a limits -1 to 1. So definition, even order function, we need to check, but here I will solve directly. Okay, so we are integrating with respect to y. So integration will be y. Integration of y is y square by 2, and integration of z is zy -1 to 1 dz. Okay, so -1 to 1. I am putting 1 first at a place of y. So we'll have 1, 1 by 2 and z. I will put -1 everywhere at a place of y. So here -1, square of -1 is 1, here -1, okay, dz. This is equal to -1 to 1. So here if you add 3 by 2 plus z minus. So if you add -1 by 2, right, and minus minus plus 1 by 2, and z, see, minus minus plus z dz. So -1 to 1. So if you add 3 by 2 plus 1 by 2, 4 by 2, which is 2. Z plus z, 2z. So let us integrate. Integration of 2 is 2z. Integration of 2z, 2 is constant. Integration of z is z square by 2. 2 will get cancelled, and simply we will have z square -1 to 1. I am putting upper limit first. So 2 plus 1. I am putting lower limit now. -2 square of -1 is 1. So this is 3, and this minus minus plus 1, which is 4. So that means line integral, okay, sorry, surface integral of a scalar field f over S1 is 4. So let us work on S2 now, okay, make a screenshot of it first, then I will go further. So let us work on S2. So S2 is a surface, you can easily see, which is on the back side of that getting cube S2. So its equation is x is equal to -1. So as you know, we have 6 surfaces having equation x is equal to 1, x is equal to -1, y is equal to 1 on this side, y is equal to -1 on this side. At the top we have z is equal to 1, and at the bottom we have z is equal to -1. So equation of S2 is x is equal to -1. Okay. So the next important thing is parameterization. So let us find parameterization of S2. We will denote it by phi. As you can see here, x is -1. So that means value of x is fixed. So y and z can vary. So again I can write here phi of yz. Okay, so let me tell you for the remaining surfaces. Okay, if you have equation of surfaces z is equal to 1. If z is fixed, that means x and y can vary. So you can take here x comma y. But for S2, x is fixed. So that's why y and z can vary. So that's why I'm taking y, z. Okay, so phi of yz, which is equal to x is fixed, which is -1. And obviously I will write yz. So here y and z can vary. These are parameters. So I should have the limits of y and z. So will you tell me what will be the limits of y? In a problem they have mentioned it is -1 to 1 and limits of z are -1 to 1. Okay. So after that what will I do? See, you remember the definition, okay, definition of that surface integral of a scalar field. Okay, that definition, some things we want. So let us find all these things one by one. After having phi, I will go for derivative of phi with respect to y. So its derivative with respect to y, derivative 0, derivative 1, derivative 0. Derivative of phi with respect to z, constant 0, constant derivative 0, its variable derivative of z with respect to z we will have 1. After that we go for phi y cross phi z. Okay, so the cross product we have, that means we have to solve a determinant. What will be the first row? Obviously ijk. The second row, these entries we should consider. Third row, these three entries we should consider, right? So let us solve. I, product of this to 1 minus product of this to 0 minus z, always middle term has a minus sign here when you solve the determinant. Product of this to 0 minus product of this to 0 plus k, 0 and 1 into 0, 0. So that means let us see finally what we have. Let me write here. Okay, only the multiple of I is 1 non-zero number and the remaining z and k have zeros multiples. Okay, so I plus 0j plus 0k. After that what we want? We want its norm. Let us find its norm. So norm of phi y cross phi z. So you know well what is the definition of norm? Square root of multiple of I, which is 1. So square will be 1, square of 0 is 0, square of 0 is 0. So the value is 1. Let us find the next term, that is phi of f of phi of yz. F of, what is phi of yz? Yes, it is -1 yz. Let me put its value, -1 yz. After that we have to operate f on that. Let us follow the definition of f. It is very simple, x plus y plus z. That means simply we have to add these components of f. Okay, so this one, so -1 plus y plus z. Now I will follow the definition. So therefore double integration of f over S2, the definition says double integration, right? F of phi of yz, norm phi y cross phi z and dy dz. See, I should write limits of y and z here since we have a parameters yz, right? So what are the limits of y? -1 to 1. Limits of z, -1 to 1. So this is equal to -1 to 1, -1 to 1, f of phi of yz. Its value we have calculated, -1 y plus z. Value of norm is 1 and now I should write dz. Let us solve this integration. First make a screenshot of it. So let us simplify it further. Okay. So as you can see, we have a limits -1 to 1. So definitely we can go for even odd function. But again, I will tell you, I will directly solve this problem instead of going to even odd function. We can solve it in that way also. Okay. So first of all, I will integrate with respect to y. Integration will be -y. Integration of y is y square by 2. Integration of z is zy with limits -1 to 1 dz. So I am putting upper limit first, -1, 1 by 2 and z. After that I will put lower limit -1, minus plus, square of -1 is 1 and here we will have minus z, okay, dz. So this is equal to -1 to 1. Let us add. So we'll have -1 by 2 plus z. If you add them, you will have 3 by 2, but there is minus sign. Minus plus z dz. So this is -1 to 1. Getting? So let us simplify it first. -1 by 2 minus 3 by 2. Both of them have the same denominator 2. We can add numerators. -4 by 2, that means -2. Z plus z 2z. Let us integrate with respect to z. Its integration will be -2z. As you know, the integration of z is z square by 2. 2 is already there, it will get cancelled. So z square, -1 to 1. Putting upper limit, -2 plus 1. Putting lower limit there, we will have, yes. So it is minus 1 and this is minus 3. So it is minus 4. So the surface integral of f over S2 is minus 4. Okay, surface integral of f over S2 is minus 4. Similarly, we can go for S3, S4, S5 and S6. Okay, so simply we will discuss. Okay, so you can solve on your own. I am going to write directly the values. Okay, for S3, what is the equation of S3? This is our S3. Its equation is y is equal to 1. So the parameterization will be, let me simply tell you what will be the parameterization for S3. So S3, its equation is y is equal to 1, right? Y is equal to 1. On this side we have, so parameterization will be, so x and z will vary. X and z will vary. So phi of yz is equal to x, y is fixed 1, z. Okay. X and z are varying. So I should write the limits of x and limits of z. So these limits are already given in problem. So no need to worry about it. S4. For S4, the equation is y is equal to minus 1. So the same parameterization will work. Simply, we have to replace this 1 by minus 1. Similarly, you have to do for S5 and S6. So here I am going to write the values directly. Make a screenshot of it first, then I will go further. So I have written the values directly. Okay. So values of double integration of f over S3 is 4, on S4 minus 4, on S5 4 and on S6 minus 4. Then double integration of f over S. Okay, surface integral of a scalar field f. As I told you earlier, it is over S1 over S2, double integration over S3 and so on S6. Let us put the values. Over S1 we have 4, over S2 minus 4, over S3 4, over S5 minus 4, S4 sorry, S5 4, S6 minus 4. So all terms will get cancelled to each other and the final answer is 0. Okay, make a screenshot of it first, then we will stop. Thank you. See you in next video.